Hello everyone, here is the solution for problem 2 in homework 10. We want to collect the definition and properties of stochastic process. Firstly, for the WSS. So the definition is that its mean is a constant. And the autocorrelation is a function of the time difference. We can note that the WSS only use mean and autocorrelation. In practice, they are much easier to get than second-order density. Based on the mean and the autocorrelation function, we can do many things already. We can do state estimation, parameter estimation, and prediction in mean-square sense. In communication application, in most cases, we do not care too much on a specific value of the stochastic process. We pay our attention on the power of the signals. The autocorrelation function RT1, T2 for T1 equals T2. Therefore, it is RT1. T1 is the average power of the signal at T1. We see that when the input is WSS, the output, a stable LTI system, is also WSS. Then we want to show the definition and properties of independent increment process. The definition for that is which means xt1 to minus xt2 and xt3 minus xt4, and they are non-overlapping intervals. Then the two random variables are independent. So far, we see that the Poisson process, random walk, and Wiener process are independent increment process. It seems independent increment property is somehow related with Markov process. Third, we want to show the definition of Markov chain, a Markov process. So it means that the past has no influence on the future, and only the present related with the future. So far, we see that Poisson process, Poisson impulse, semi-random telegraph, random walk, and Wiener process are all Markov process. So actually, in real world, many processes have Markov property. So fourth, we want to show the normal process, where the Gaussian process is a special case for the normal process which satisfies the Gaussian distribution. So the definition is that the process xt is said to be normal if the random variable xt1, xt2 to xtn are jointly normal for any n, any t1 to tn, so which is fx x1 to xn, t1 to tn, which is equal to the jointly normal distribution. So the statistics of a normal process is completely determined in terms of the mean, eta t, and the autocorrelation RT1, T2. In general, Nt is a function of t. In this course, we classified Wiener process as one example of stochastic process, and we classify normal process as a property of stochastic process. That is, we treat normal process as a larger class of stochastic process and treat Wiener process as a specific example. So fifth, a process is we want to show the definition of strictly stationary process. So the definition for the SSS process is statistic is not affected by a shift on a time axis. So we want to write the formula for the SSS, which can be written as 2xn t1 to tn is equal to fx x1 to xn and t1 plus epsilon t2 plus epsilon until tn plus epsilon. So actually, whatever the number of epsilon is, the jointly distribution will not change, and this condition is really hard to meet. So 6, we want to show the white noise. So for the Wiener process Wt, we want to discuss its derivatives, which is denoted as dWt dt, and we will have the expectation of the derivatives is equal to 0. And the autocorrelation T1, T2 is equal to alpha times delta T1 minus T2. So actually, when the process does not have derivative, we use this just as a notation. Then we need to do further discussion. Instead of Vt dt, we use dWt. Wt is continuous with probability 1. It has differentiable dWt. Vt dWt dt is Gaussian white noise with zero mean and impulse autocorrelation function. Well, we should define more general white noise with zero mean and impulse autocorrelation function, so that a stochastic process Vt is said to be white noise if its expectation is 0 and the autocorrelation is an impulse. It's a function of qt1 times impulse. Seventh, the stochastic process xt is said to be mean Gaussian process if the following property holds. The limit of t to infinity 1 over 2t negative to positive t xt dt, the expectation of xt in mean square sense. So at last, we want to show the definition of martingale and the discussion. So what is a martingale? The formula for the definition can be written as the expectation of xt on the condition of xs equals to x1 is exactly x1, where s is smaller than t. It means that the conditional mean equals the condition. This is true for random walk and winner process,